This is part E of the gas law's notes. We are going to talk about the combined gas law in this section of notes. So the combined gas law combines all of the relationships we've already talked about. So the relationship between the three gas variables of pressure, volume, and temperature. And for this, we are again looking at when an amount of gas remains constant. And as we look at this, we have seen that pressure volume relationship in our second set of notes that was talking about Boyle's law. And so if our temperature isn't changing, we can get rid of just those temperature variables and we end up with that Boyle's law. If we are just looking at that pressure and temperature relationship and volume isn't changing, then we're able to just cancel those out and we get Gay-Lussac's law. If we are looking at just the volume temperature relationship and our pressure doesn't change, we can get rid of pressure on both sides and we end up with that Charles law. And so this combined gas law, though looks at, well, what if we are having pressure, temperature, and volume conditions that all change? And so it relates all of those variables. Because of having both direct and indirect relationships, and we might have maybe pressure going up, but temperature going down, we don't generally model these relationships because we have all three variables that are going to be changing. Example 1. A gas initially has a volume of 22.0 liters and a pressure of 30.7 kPa. If we change the pressure of the gas so that it has a final volume of 18.99 liters, what is the final pressure of the gas? Assume the temperature of the gas is kept constant. And so we could have seen, and we probably did see a problem similar to this in one of our other sections, because if temperature of gas is staying constant, we can actually just remove that from our formula because we are basically just dividing each side by the same number. And so that's how we can go ahead and get that volume and pressure relationship from this combined gas law. And so if we're looking at it, we have an initial volume, so V1 of 22.0 liters. We have an initial pressure of 30.7 kPa. Those are in our standard units. And then we have a final volume of 18.99 liters. We're finding, well, what is going to be that final pressure? And then we can go ahead and just grab the top of this relationship. We don't have to divide both things by the same number. That is going to stay constant. So that would really, the temperature would cancel. And so we're going to have our 30.7 kPa times 22.0 liters equals that 30.7, P2, what we're looking for, times that 18.99 liters, plugging everything in, and then we can solve. So how do we get P2 by itself? Divide both sides by that 18.99 liters. And we can see again that when we have those standard units or those matching units, our units are going to cancel for liters on the left. These completely cancel, and so we can find, well, what is that resulting pressure? Looking at sig figs, it looks like we have 3 sig figs we want in our answer, so P2 is going to end up being 35.6. And again, we have that unit of kPa left, and those kilopascals are our standard unit for pressure. And so that's how we can use that combined gas law that's on our formula sheet in order to get any of our other 3 relationships where we just have 2 variables changing. We could, though, have all 3 variables changing, so let's look at example 2. A gas has a volume of 26 liters and a pressure of 297 kPa. with an unknown temperature. So we have a volume, a pressure, and a temperature. The volume of the gas was increased to 34 liters. Temperature is decreased to 35 degrees Celsius. The pressure after the change is 220 kPa. So what is the original volume or original temperature? And so when we're looking at this, we have two volumes, we have two temperatures, we have two pressures. And so we have all three of those variables. We need to just make sure as we're organizing these, P1, V1, T1, it doesn't matter which of these I make my ones and my twos, but I just need to make sure that these are all conditions that are happening at the same time. Same thing then with my P2, V2, and T2. And so sometimes I think it helps to just organize by writing out everything that I know and putting that writing out those values that my problem gave me. So 26.0 liters, liters is our standard unit of volume, so that's good. 297 kPa, that is kPa's pressure. Unknown temperature, we're looking for T1. P2, we have 220, or I guess I can just go through read my problem. The volume is increased to 34 liters. Its temperature is decreased to 35 degrees Celsius, and the pressure changes to 220 kPa. We haven't had to do this one yet, but we need to make sure that our temperatures are in Kelvin. And so in order to get that to Kelvin, and this is on your formula sheet, we're going to take our degrees Celsius and add 273. So plus that 273, our T2 is 308 Kelvin. And that's going to be what we need in order to get that temperature out, the initial temperature in Kelvin. Now I can take that and plug everything in to my formula in those appropriate spots. So 297 times 26.0 divided by, I'm looking for T1. You can use T1, or if you'd prefer to write a variable. And then we've got equals 220 times 34, and this is liters, divided by our temperature in Kelvin, that 308. Use whatever algebra skills you have to solve. I like to think of it as cross multiplying, but you can always just put all this into your calculator, multiply this out, and then when you have something with more simplified values, rearrange to get t by itself. Otherwise, I like to do that cross multiplying, so I'm going to multiply 297 times 26.0 times 308, and then that's going to equal T1 times 200 times 34.0. To get T1 by itself, I'm going to then divide by whatever is on the side with it. And that means those will cancel on the right. And then I can go ahead and plug that into my calculator. I do have to be careful. I need to make sure I'm dividing by both that 200 and that 34. So if you want, multiply those out first before you do that division. And then we should get 317.96 is what I get from my calculator. Let's look at our sig figs. And if you maybe have been doing math along the way, you can't just look at your work, but you can always go back to your starting values that we have for sig figs. I like to look at these here. So we have 3 sig figs, 3 sig figs, 200 with a decimal is 3 sig figs, and 3 sig figs. So let's keep 3 sig figs in our answer. We're going to keep the hundreds place, the tens place, and the ones place. So let's look if we need to round our 1. That's a 9. So 318, and then we need to make sure we have that unit. Kelvin is our temperature 1. If you are including your units on all of your values, kPa, liters, Kelvin, 200 is kPa, and liters, then you should see those variables canceling, so you're left with just, sorry, not the variables, the units canceling, so you're just left with the unit that you need in your final answer. All right, I think sometimes with these, the trickiest part is just organizing the information. Go ahead and read problem number 3 on your own. See if you can get all that kind of organized, and then check with how I organize that problem. And then when you're ready, pause the video and then come back to see what the answer is. I've got the setup and then my math there. My final answer for number 3 is 7.41 liters for the initial volume. Reach out to your teacher with any questions.